So I've done this a few times. It's whether I stutter, my voice cracks, my headphones break or turn off. They haven't broken yet, but they've turned off. Or my parents walk in the room, which means you can hear my parents in the background saying some Latino stuff. Not trying to have that happen in my video. Today, I'm going to be talking about Graham's law of effusion and diffusion. The way I'm going to explain this is going to be weird. So, to help me, I'm going to be using a simulation called the Powder Toy and Microsoft Paint. You got to use what you got. Let's go. So let's start off with diffusion. Diffusion is how a gas equalizes in pressure throughout a volume. So I'm going to put some noble gas here. This is a noble gas. Doesn't do anything. Not going to melt my glass encasing. All right, this is glass. It says right there. That one. All right. Also, the pressure's right there, so watch it. Wherever I move my mouse is what the pressure is going to be. Right now it's 0 because nothing's happened yet. So when I unpause this, the gas is going to expand, and eventually it will equalize in pressure, right? The speed in which this happens is called the rate of diffusion. Okay. According to Graham's law, the rate of diffusion increases as temperature increases, right? This happens because say there's a molecule and it gets heated up. Here's some fire. There's fire. Blah, blah, blah. All right. So there's fire. The kinetic energy allows this molecule to move faster, which allows it to diffuse faster and equalize the pressure inside of the encasing. All right. So that's diffusion. Basically, the way uh, molecules disperse in pressure throughout a given volume. As you can see, the pressure is around 3.03, 3.02, right there. All right, so this is a diffused gas. It's diffused throughout the entirety of this glass encasing. Now we're going to talk about effusion, right? Basically, effusion is how a gas expands through, or goes through a tiny little slit or hole to diffuse both sides of the volume, right? This is what's blocking both of the areas, right? The way effusion works is it is increased. The rate of effusion is increased with temperature. It is also increased with how small the molecules are. Right now, these molecules are effusing into the other area, right? Rate of diffusion and effusion go hand in hand. Stop that. All right. So if you have a tiny molecule, it's going to be a lot easier for that tiny molecule to find its way into the other, through the hole and into the other encasing, right? Another factor that affects the rate of effusion is the kinetic energy or heat, right? So if this diffuses fast due to the heat, then that means the molecules will be bouncing around a lot faster, right? The kinetic energy is causing it to bounce around so fast that it finds its way through the hole faster, right? So the rate of diffusion and the rate of effusion go hand in hand. Another thing that affects it clearly is the size of the hole. So if you have a tiny hole, then molecules would be it'll be a lot harder for the molecules to like actually like land in that tiny hole. But yeah, that's about it. That is effusion. Effusion is basically the rate in which molecules go through a tiny hole, right? And then diffusion is how fast the molecules disperse into equilibrium so that the whole area is the same pressure. Um, that's about it. Uh, things to note, temperature and rate of diffusion uh, go hand in hand, and the rate of diffusion go hand in hand with the rate of effusion. So that's about it. Um, I hope you liked my presentation video. Good voice crack, Andy.